Hey everyone, let's take a trip up Highway 1 to Morro Bay to check out the dynamic system of sailing dinghies. For this system, the inputs are wind angle, wind speed, and heel angle. The crew acts as the controller. An interesting part about this system is that the sailor is the input and controller at various times. We're going to examine a special case where the dinghy is traveling in a straight line and the sailor is only acting as a controller, not an input. Additionally, for disturbances, we have wave and wind oscillations. All of the previously mentioned things act on the plant, which in this case is the boat, and its outputs are boat speed and change in heel angle. The boat's velocity, sail, rudder, and heel angles, as well as the crew's weight and placement, work to change the boat's heading, to make it go fast.
First case, let's look at the system when we're sailing upwind. It's important to note that a sailboat can't actually sail directly upwind. It must go back and forth around 40 to 45 degrees off the wind direction. The upwind mantra is flat is fast, so the equilibrium point is when the heel angle and angular velocity are both zero. The wind is trying to tip the boat over, which is coupled with the blade running through the water to create a moment that must be resisted by the weight and lateral displacement of the crew. Magically, the boat moves forward because of the resultant torque. For max VMG, velocity made good, which is the velocity in the wind direction, the boat needs to maintain its optimum angle relative to the wind angle. If the wind shifts in either speed or direction, then the crew needs to return the system to its equilibrium point by hiking out if the velocity increases, or turning the tiller if the direction changes. The proportion of this response is controlled by the crew and is based off of their perception of the heel and wind angle velocities. Too slow of a response means losing time spent at max VMG, but too large of a response means the rudder will slow the boat down and also the forward momentum will not be transferred to the boat on its new heading. Humans also make good derivative controllers, since the response overshoot from the steady state value is usually non-existent.
For the downwind case, we're going to assume a constant wind angle directly behind the boat. The sail is not generating any lift, it's just getting pushed by the wind. You are ideally using the whole force of the wind to propel you forward. There is no magic moment coupling, it's just the straight force pushing you. The control for the downwind case is the same as it is for the upwind case, with the crew sensing the boat is moving off course and correcting. The equilibrium in this mode is very unstable in the roll direction, since the boat is artificially heeled to windward in order to reduce the hull's wetted surface area and raise the sail area higher into the free stream. Derivative control is crucial to avoid death rolling, where the boat capsizes and violently decelerates as the mast hits the water. The destabilized system rocks back and forth, usually due to high winds, which is exacerbated by any response overshoot, so the crew must mitigate the penduluming response.
All in all, sailing is a great example of a controlled dynamic process with a feedback element. Additionally, we'd like to thank the Cal Poly Sailing Team and the Morro Bay Yacht Club for the use of their materials and facilities. And a bit of advice from the crew: if you like it, tie it down, and if you love it, don't take it sailing. Happy sailing, everyone!